Then we can get started. So welcome to our Data World Tour, the 7th and final stop. That doesn't ring a bell maybe to everybody. So Darwin organized a Data World Tour, which is, 7 stops of various meetups, all relating data science. So previously we were at Munich, Berlin, Zurich, Copenhagen, Boston and New York. And to finish up with a bang, of course, the last stop is Amsterdam. We got a few people hopefully watching on the live stream, millions of people watching there. Also welcome. So that is why we are here. I first want to give the floor to Joost, who gave us the opportunity to facilitate the whole meetup here. He will explain why he's welcoming us, and then I will pick it up again. Wil je wat langer praten? Dan is het wel.
Okay, just a short one for everybody. Very welcome in our office, our Future Facts item office here. Maybe some of you know us already. Item and Future Facts, we're a data-driven company consulting with our clients for over 20 years already about data-driven subjects, of course. Last 3 years, together with Adil and Darwin, we founded Future Facts, business analytics company specialized in data science and big data. So we're in the right place to have a very interesting evening, and we're all enjoying our lovely work, of course. So hopefully, nice speakers over here, and enjoy the evening for today.
Perfect. Thanks, Joost. So maybe it's for some of you a little bit odd that Darwin is organizing this. So I just wanted to go through with it the reason why we wanna build a little community around data science. Well, basically it's because we see that as the future, and it will be massive for all you guys who are interested, but also for us as a specialized agency. So just a quick introduction. Darwin started in, it's now 17 years ago in the UK, in Billericay, a little city near London. Always specialized on tech and telecom recruitment. 6 years ago we opened the Amsterdam office. I'm there working now for nearly 3 years. And recently, or 2 years ago, we also saw that at least AI will be the future. For you and also for us in terms of making a difference in the field. So that's why, as a consultant like me, I want to specialize in it. I'm specialized, you will see it, the pictures later. I was always specialized in software engineering, Java, Scala, and now I'm focused on data engineering. My colleagues somewhere in the crowd, Nick and Rodri, yeah, they're great guys. They will be focusing on data science more and more. Specifically focus on the Amsterdam business. And I mentioned already, we were also present in Copenhagen, Munich, Berlin, Boston since the beginning of the year. So these are all offices on different countries we work on, to make a difference and to hopefully be the recruitment brand for AI in the future. And that's why we started with it now. We have the live stream set up. You can watch it back. You can also replay all the other live streams. We will send a link afterwards via mail. Maybe we can also put it up here. If you missed anything, or you thought maybe the speakers at the other meetups were very interesting, watch it back. It's all possible. You maybe see this. So this is a little competition we got going on. Well, you don't really have to compete for it. You just need to sign up. So yeah, no sports, no activities, just to sign up to win 2 tickets to Data Natives. A sort of conference on big data and data science. Data Natives, they have given us the opportunity to give away 2 tickets to the winner. They also contributed to the flights, and Darwin will organize the accommodation for you. It will happen the 22nd and 23rd of November, I think. So if you win, you can bring along 1 person and have a great day. So make sure you sign up. That's with the piece of paper you got in front of you. So leave your details, and then you have a chance to win and to visit the event. Last thing, and then I will stop talking because you're not here for me, but for these guys in the front seat, and Agis, who is somewhere there. Yeah, hi. So this was the start of the introduction with me, same jacket, so you can recognize me. First up will be Eduardo from IBM. Then we have a little switch over to Floris and Jan sitting in the front row. They will do it together, and we end off with Agis to have his presentation. If you have any questions, we're going to do a little QA session after each talk, just quickly, if there's anything you want to talk about. Or maybe you prefer to have a discussion during the presentation, that's up to you. So right now, I want to give the floor to Eduardo to get started. We need to fix things with the presentation, so give us 2 minutes and then we're ready. Yeah.
So just pretty straightforward. That goes in your pocket, and if you could put that just as close to your. Yeah, or your pocket, yeah, just in case it falls out.
Yeah. Okay, yeah.
Bits.
So get my phone.
Hopefully you don't need that.
Yeah.
Right.
Is that okay?
Yeah, it should be fine. Do you want to just pop that on?
I just put it out and in again. So.
That's what happens. That's what happens. The other one, yeah. They've got two small screens. Do you have the?
So I just got it out.
Yeah, take it out. It should automatically switch over. This is the only. Right, there we go. Is it coming on? Even when you test it. Even when you test it, yeah, nothing ever goes right. Oh,
yeah.
Perfect. Okay. We'll get there eventually.
Cool.
Okay, perfect.
Thanks. Okay. So hello everybody, my name is Eduardo. Can you hear me? Yeah, right? Also here is okay? Cool. Yeah, so I'm a data scientist with IBM, and I'm pretty sure this is going to be the easiest talk of the evening, so enjoy. Who am I? I joined IBM a couple of months ago, actually, as a data scientist. I'm pretty busy with recommender systems. I also like to do quite some work with theory-guided machine learning, try to couple, let's say, physics with machine learning. Before working with IBM, I did a couple of years with Mobiquity, which was also consulting. Similar work to what I do now, and before. So my background is not in machine learning originally. I studied physics, and then switched to data science. So tonight, what are we going to do tonight? The idea was, so can we actually understand or actually explain to people what we do in a, let's say, better way or more effective way? And I guess to actually do that, we should be able to understand how did it all started, where are we now, and possibly future applications towards, okay, what is it going to go? Can we have any control on it? Are we approaching a second hype wave where people are expecting tremendous amounts of results? And are we able to deliver those types of results? So if we start yesterday, I mean really yesterday, I'm not talking about kind of 3 years ago. So in my mind, data science and machine learning and all those things, this is natural extension of mathematics and physics and that type of work that folks were doing in the 1600s, right? So we have a pretty long journey up to we get to today. But you see here the first sparkles of, okay, on the left you see the Principia Mathematica from Isaac Newton. So kind of establishing how we understand modern mathematics as we do today, so integrals and that type of thing. On the right here, you see the first mention to binary systems, right? So that's still the type of thing we are pretty much doing all the time. And this is from, once again, 1694, 97 or something like that. So this lays the basics of where we are now. So it's not such a mystery. Where are we going? What is it going to be? No, it's actually, this thing has been developing for quite some time. So if you move a little bit further, you have that, so physics was one of these fields where they were struggling with too much information. So how can you actually combine this type of information? And Fourier came with a very nice idea of Fourier series that we all, I mean, in physics, people are really using that quite a lot. And you also have Fourier transformations in convolutional neural nets and that type of thing. So in data science, we are very much busy with that. So mathematics was used as a tool to describe nature. What is a pretty fascinating thing, right? This one on the right is also familiar to most of you, I guess. So this was a development in terms of Boolean algebra. So all the ones and zeros and the combinations and how can we understand this system. So this is pretty much the basics of every programming language that we have. And yeah, well, going a little bit further because we don't have 3 hours. If you go to the 1900s, Alan Turing so he came up with a formalization of what an algorithm is. He created the Turing test, of course. I wonder if he called it Turing test back then, but he came up with that very well-known test that we don't have to describe here. But then computers started to pick up, and a certain hype came with the space race, right? And IBM was very much involved into that, and with the concept of super computers, right? And this started back in the 1950s. So if you see here, well, you don't. Well, here you see that things are pretty much separated. And then with time, if you look at things like computer science and visualization or mathematics or statistics or even physics, I could include it here, you see that things starting to get mixed and starting to get closer to each other. So this type of mechanism helps us to understand where are we going to go. And the answer is it's going to be all a big mess. So where everything is going to be connected, and that's why we have a job. So we have to make sense of all these things together. Right? Okay, so, so yeah, if you go back to the 1950s, then you see, well, folks looked at neurons and they were like, oh, wait, if I use that binary thing, we can do that in a computer too. And so they did. And this works really well, but the question was, were they satisfied with that back then? So they understood that you could get a neuron working with a pulse, with an electric pulse, as biologists know for many, many years. And then some smart guy said, well, we can use something called an activation function and actually make sense of it. Then in the 60s, decision trees, I guess everybody here, or at least the data scientists, use XGBoost or even slightly similar random forest, those types of algorithms. Very old concept, So the question is, why is it only now? Why only now? Why are we talking about those things only now? They were developed in the 50s, in the 60s, and in the 70s, and in the 80s, and then it was a gigantic hype, and everybody was excited and over-promising things, and oh, those guys can do it in 30 minutes, and that sounds familiar, right? What is a little bit scary, because what happened immediately after was this. They had all these brilliant ideas, but then nothing worked. They just couldn't get it done. They would do predictions, and the predictions would be just not good. Business will say, oh, great idea, man, but thanks, it doesn't work. And this was very sad. This went on for 20 years at least. So people lost faith of neural nets, and even if you look at academia now, there is some sort of barrier between what is real science and well, you guys like do brute force answers through a computer, right? And why that didn't work? So, you know, there are economic factors, so not a lot of funding going on, so the world was not in its best at that time. The computers were just not powerful enough. So this guy said that in the 60s. And what I don't like about that is that if I read that now and I write 2005 or 2010, that sentence still makes sense. And you just replace first by second. So that sentence always bothers me a little bit. So my question is, are we going back to a second wave of hype and overpromise and we can do everything type of thing? So where are we today? So things started to get more and more powerful, right? Computers started to develop, people got excited, more and more technology. So I was born somewhere here, between the Apple and the Pentium computer. And yeah, so in my lifetime, that's a pretty big jump, I would say, compared to someone who was born in the 40s or in the 50s, where not so much was going on. So then this concept of machine learning, which is not a new concept, but it started to pick it up, right? So as systems that automatically learn programs from data. And that's quite of a fantastic concept, because people were very much used to, if you look at physics, for example, learning from observations, right? And deriving formulas. And just, you are learning from a certain phenomenon. And that's a whole different paradigm, because it doesn't matter what it is, you're just learning from the data. So you are not modeling processes anymore. You're modeling data. And that's a pretty important thing. So moving on, these things started to pick it up, right? And the ones who are old enough will remember this. This was a classic. This is a classic picture where computers started to, okay, we may be a little bit smarter than people doing one specific task. And yeah, I mean, this worked out well, not for Gaudi, but for IBM. And, you know, things kept developing. And so if you look now, we have all these chatbots and all those things going on. IBM Watson and Alexa and just recently the AlphaGo thing. So things are kind of heating, right? And the issue now is pretty much, now we just have a lot of data. So companies just have a shit ton of data, and they don't know too well how to handle it. And to be honest, a lot of the data science folks also do not. So this new data engineering thing started to you know, like, hey, we can save you, data scientists. We know how to use you know, certain types of technology or use the cloud, or you know, get your data in buckets or whatever technology you were looking at, and try to make sense of all of these things. And then this concept of cloud got quite a lot of attention. And prices were abusive a couple of years ago. Now prices are getting cheaper and cheaper, and storage is extremely cheap now. And then we'd say, okay, well, we kind of figured that out. Not really, but we are going towards understanding how to store and how to process and how to modify data relatively fast. But then what is the business doing with it, right? So if you look, the problem is that people think that these systems will be autonomous systems and they won't need people to look at them and to make sense of them. And this Nate Silver, he's a statistician that most of you probably know, and then he says when human judgment and big data intersect, there are some funny things that happen. And that's true, right? But for some companies, analytics was not the core of their business, but was something that was attached to it or forced to it. And I guess that we do need to understand now that analytics is pretty much, data-driven companies, as everybody calls, it should be the sustaining element of every healthy company who wants to still be around in the next 10 years. And well, it's not really a nice to have anymore. It's not something to be proud. Like my company does analytics. That was 10 years ago, right? So, but still, if you see from moving from descriptive analytics, so for the what happened question, all the way down to the prescriptive bit. So we are, as data scientists, we are interested in those two blocks here, where we are going to look at what will happen and how can we make it happen. There are a bunch of new algorithms coming and quite some fantastic stuff going on. But this is extremely hard. So a lot of companies are stuck in the first two blocks, in the what happened bits, and struggling with visualizations and struggling with with BI stuff, even though we should have figured it out by now, I would say. How are companies using that, right? Now, as I said, so the cloud thing is kind of okay. So we understand cloud systems, and business is really using data science, what is a great thing to see. You have Duolingo, or you have, I guess, Nike there using a app to promote health. So make sure you go running, even like go drink water. So all these crazy things that now there is machine learning and everything, right? This is something that that I actually did, was to come up with a model to predict car pricing here in Holland. And giving a car and giving the features of a car, you could come up with a price to help the dealer to make sure that the car doesn't remain in stock for 3 months and no one buys the car, and then he needs to sell the car for a very low price, and then he loses all his margin, right? So can we come up with such a model that has previous prices as input? And I mean, this is just a simple regression problem, right? With so many features, but this was an interesting problem to couple with the business knowledge and to get into a very traditional industry, like the automotive industry, and help them make sense of their data. So if you look at recommender systems, which is also something that I quite like, they do work, don't they? So we're going to hear something, I guess, later about recommender systems, which is quite nice. A lot more technical than this presentation. But I mean, you see, like, Amazon recommending stuff, and you see, Spotify. IBM is also doing that with many clients. I just picked up one where we are helping them with recommending roles for the personnel. So making sure that they have their access limited to the type of access they should have, and not let them having too much access. So that's kind of an unrecommender system. So that's a interesting concept as well. Not too much literature on unrecommender systems, but that's something else that IBM is actually doing, is to helping build on physical knowledge and solving engineering bottlenecks. So we are busy with the implementing a machine learning methodology to forecast seismicity in the Groningen field. So this is a kind of effort which we share with the NUM. So for the Dutch people in the audience, we know that's a very sensitive topic, and both companies are really taking that seriously now and trying to understand how machine learning can help physical models to make more sense or to make better predictions. Yeah, so then the message is, okay, giving enough data, the system will improve itself and learn to take better decisions. And the question then is, what is a better decision, right? Then folks talk a lot about privacy, right? So, transparency so this is something that AI really has to develop, is to make sure that we focus on safety, on security, and on ethics as well, right? Why do I say that? Because at the state of the art now, it becomes complicated to use that type of model to, let's say you build a fancy neural network to predict if someone should get a mortgage or not. That should be a straightforward problem, right? We have data from the past. We know if people pay their mortgage or not. We know their data. But let's say that then the model says no. And then you're going to get a letter at home and saying, well, neuron 27 didn't fire up, so you're not getting a mortgage. We are sorry. So we are missing quite a bit on also on the explanation of things. So how can we make more sense of the type of models we are actually building? Okay, it's not working anymore. Okay, so if you look at tomorrow, and obviously this is pure speculation, right? Because it's things we don't know. So I would like to start with asking, so let's start very simple. Who likes classical music here? Anyone? Any fans of classical music? Cool, a few hands. So I would like to play you a well-known piece of music, and I would like you guys to just tell me who wrote that. So this one should be straightforward because it's well-known. Who wrote that? You can like guess also, right? It doesn't matter. Bach. What else? We have one vote for Bach. Huh? So I mean, so this is actually everybody, right? So this is not a well-known piece. I was lying. This is a this was actually done by a AI that took as input pieces from Bach and from Mozart and from Chopin and made sense of all of it. And the objective was to predict what is the next note and when. Right. So they kind of used all that type of music to come up with with classical music. So this is a nice way of also seeing how the applications in the future of machine learning is not only on, you know, destroying the world, and you can do cool things like that too. You know, you can also discuss with people now with artificial intelligence. Who saw that? Nobody saw that? One person there, cool. IBM is not doing too well in the marketing bit, I see, is it? So let me try to show that to you guys. So this is actually to help oh, that's something else. Oh, that doesn't go like that. That's AI.
By the candidates themselves.
What we are trying to accomplish here is really to demonstrate that we can have a meaningful and valuable discussion between man and machine.
We are actually trying to show that a computer system can add to our conversation or decision making by bringing facts and doing a different kind of argumentation.
Hello, Dan. Thank you for the opportunity to be here today.
The debater system tries to understand the concept over which we are debating.
Having analyzed the data, I will argue that we should subsidize music education.
When it gets the topic, until you hear the first speech, it's collecting all the possible arguments, trying to remove redundancy.
It is about recognizing important issues for society.
The system is evolving.
The IBM debater can have all the opinions in the world, but IBM debater does not pay taxes, and we do.
You are speaking at the extremely fast rate of 218 words per minute. There is no need to hurry.
The value of the technology is really to allow decision makers to take more informed decisions. There is a territory which is uncharted to some extent, and this is where we are now.
Thank you for listening.
Okay, so that's kind of cool, I thought. When I first saw it, I was like, okay, that's a nice idea. But, you know, people still have the impression that this is to compete, and that's to help. That's to be one extra seat in that room making a decision, right? And that's very different from, oh, let's exclude everybody, and let's just put one debater, and we are good. It's not at all like that. So you can also have less harmful future applications of artificial intelligence. So this is a little something that I did. I live in Alkmaar, in the north of the country, and that painting you guys probably know, hopefully. Well, the one on the left, not. So this is a picture close to where I live, in Alkmaar, so it's a very nice square. And you can combine them and like make these cool things, right? And I call it Vincent and Eduardo. It's a bit ridiculous, but okay. It's a lot cheaper than the other one. So, you know, you can do these cool things. And if you see, I mean, even to, this is a CNN for the data science folks in the room. But this is not too hard to explain. So you just break it down both images in layers. And then you throw away some layers of one picture. And then you just take the layers on the other picture, you replace them, and then you average them together. So the magic is not in doing that. The magic is knowing what layers you are going to throw. And that need a data scientist for, hopefully. Well, I guess I'm getting on time. So, you know, you have many other things in terms of where AI is going, and you see NVIDIA and okay, let's make cars that don't need us anymore, so they can just drive themselves. You know, we can catch criminals with AI, supposedly. Trying to understand, you know, how people behave, and that type of thing in an airport would be interesting, or on a train station, or you know, all these interesting applications. And you know, now we are also struggling with with making sense of things. So can computers understand what we're saying, right? Sort of sentiment analysis or that type of thing. So this is a new paper on trying to understand sentiment mining, he calls that. And you know, the question is, when you look at this, like a sentiment engine would say that's a positive sentence, and is it? Right? I mean, even though that's very straightforward to us, but for a computer, that type of, you know, sarcasm and those things, this is extremely hard to make sense. So, you know, this whole thing is to kind of try to kind of look at this question. So, is it there yet? So let's stop with the hype of data science can solve everything in 30 minutes. And, you know, if they are project managers, I spoke with one project manager. If you're a project manager, it's not magic. It's not in 30 minutes. It's a process that started 400 years ago. And if you Google that question, so, you know, are we there? This is what comes. So, so yeah, are we? Thanks.
Thanks, Eduardo. Are there any questions you have about these topics? Would you like to throw into the crowd? Or are we on to the next one? Move on to the next one. Thanks. Yeah.
So if anyone wants to work after, so if anyone wants to hang around, they can. Yeah. Okay, guys, there you go. There you go.
Thank you.
Does it work? Yeah, great.
Perfect.
Yeah, can you hear me without a microphone, or should I use one? Yeah, it's fine? Okay, then do it without.
Yeah.
Well, second talk of the evening. Hope you're still awake. I'm Floris Hoogenboom. I'm working here at FutureFacts as a data scientist, together with my colleague Jan Pel. We did a case at VotingNet. VotingNet is a party that matches supply and demand for social housing in the Netherlands. Basically, we did a bit of a creative application of pairwise ranking, what we'll go into today. I was a bit curious what you were expecting from these talks, and we were a bit doubtful when preparing this, how technical should we get. So just for my understanding, who of you is expecting a talk on the business side of data science? And okay, that's great. Then I only disappoint 5. So that's already a great one. For today, I want to give you a short introduction to social housing in the Netherlands and what VotingNet actually does. Secondly, I'll show you something about the model we developed, which is basically a sort of a recommender system. So that makes Eduardo happy, probably. Then we'll go into a bit of detail on pairwise ranking, what it actually is, and how we can employ that in a creative manner. And then we'll show how we can use that to build a sort of a graph of the social housing market in the Netherlands. So understanding what VotingNet is. Well, VotingNet is actually the party in the Netherlands that matches supply and demand for social housing. And I don't know who's familiar with VotingNet of you? Okay, that's about half. Basically, in the Netherlands, we have housing corporations which own houses and which have to have the property. And we have WoningNet, which is the party that decides who should get which house. And that's based on a model that's using waiting time. So basically you enroll at WoningNet, and after 12 years or something in Amsterdam, you're eligible for a house. Yeah, that's not that great. And even more, that if you accept a house, you lose that waiting time. So basically, once you accept that, you're stuck there for 12 years. And as you can imagine, a lot can happen in those 12 years. So we set out, can we optimize this process? And I'll give you a rough sketch of what we're trying to achieve before we go into any details. But basically, if you look at the social housing market, you have, of course, a supply with people living there. And you have new entrants. And those new entrants, they don't have a house yet. Maybe they're living somewhere under a bridge, I don't know, in a box or with their parents. And basically what now happens if we redistribute the house, oh yay, I lost all my animations. That's too bad. Okay, then I'll do it without. Now suppose this person decides to move out. So this person decides, okay, I'm going to rent, or I'm going to buy a house, or rent something in the non-regularized section of the housing market. Basically, then a lot of people are eligible to apply for that house. And suppose these people all with the blue lines, they apply for that house. Then that house gets assigned to the person with the longest waiting time, which is this person of 11 years. And yeah, you can't see it that great. It's a bit of a shame. But basically, once this person moves to that house, he loses his waiting time. So he's back to 0 years again. And before he can make another move in the market, he should wait, something like 11, 12 years. So basically, what we see happening here is that with one house becoming vacant, we have made one person happy. And to make matters worse, this process of that house becoming vacant, being rented out again, on average takes 2 months here in Amsterdam. So that means that we have 2 months of living space available, which is not in use. Even more, we see a lot of people in their house who are currently unhappy. And yeah, they may be unhappy. They may be happy when they started renting that house. But yeah, maybe they got a wife, they got kids. A lot can happen, of course, in those 12 years that you're stuck there. So yeah, they're not better off. They're still in that house that may be too small or maybe in the wrong neighborhood. So basically what we set out with the thought was, okay, maybe if this person here says, okay, I actually prefer that house over my own house. And this person says, well, I prefer that house. Maybe you can find a sort of cycles in the market. And the idea with those cycles is that if everybody would follow such a cycle and everybody would make the move proposed there, then everybody would be better off. So we would have a better allocation. And there's, of course, a whole field in economics studying these kind of things. Here you have all kinds of difficulties. Like, how do you make this workable? How can you identify these moving opportunities? Well, basically, our model, we started developing with the idea of eventually identifying these kind of opportunities in the market. And we do not only want to identify those, but we also want to assign a sort of certainty to it. How certain are we that a certain move is actually an improvement? We'll come back to this later. We'll try and create such a graph structure that we can do this. But first, let me explain what kind of model we use for this. Because if we look at WoningNet, we have an enormous amount of data about preferences. And that's because we have the WoningNet portal. And the WoningNet portal is basically the website that everybody uses to apply for social housing. So each week we get a new set of houses being published there. On average, a user sees 60 houses. A user needs to be logged in before he can respond on any houses. So we also have a historic profile of what did he click on what kind of houses did he click historically, what kind of neighborhoods is he interested in. And on average, we have 40,000 unique views each week, and this is only for the region of Utrecht. So if you take the whole of Netherlands, that's even more. And of those views, we have 7,500 responses. And you should understand that a response is a bit more than simply a click. A click we see as a view, and then the user opens a house and looks at the details. But the response comes with a certain kind of obligations that if you respond to a house, you say, okay, I really want to live in this house, and I will accept this house if I get assigned to it. Of course, there are opportunities that you may decline a house after that, but that's mostly limited to 2 times. So there's really a big obligation, and this is really a good indication of the preference of a user, we think. Now the question becomes, can we identify relevant houses? And identifying relevant houses here is actually simply a basic recommender system. So to do that, we employed XGBoost, and we employed XGBoost with a very specific loss function, namely the loss function that comes from RankNet. And I don't know who of you has done ranking before. Let's see, 2, 3, okay, not that much. We'll go into what that actually means a bit later, but that specific loss function allows us to get a certain kind of probabilities from this model. And those probabilities will allow us to form a graph structure. You have a question?
Yes, I have a question about the 7500.
Yeah?
So this, so if someone, for example, has been living in a social housing for a short time, the probability that we get the house is also low, right?
Yeah.
So then this could be a bias, right?
Yeah, definitely.
Because then they would click, they would go for it, even because they are very unhappy, but then the probability is also very low, right?
That they get the house.
Yes.
Yeah, that they get the house is very low, but the probability is equally low among each houses, among all houses. So basically, there's no bias towards a certain house.
No, not towards a certain house,
yeah?
but towards how likely is someone to just click easily because it doesn't like the place where it actually lives. And given that, it's very unlikely that it gets the house.
Definitely, yeah. Yeah, and that's something we need to correct for indeed. And Jan will get to the graph structure. We have very conservative parameters there to see how we can correct for that. Is that an answer to you? Okay. So basically, we employed XGBoost, and actually we made an ensemble of a few XGBoost models, but these kind of model details don't really matter here. And what's the nice thing about the WoningNet portal is that we, of course, have those historical behavior of each user. So we can create a lot of great features about, okay, how many clicks did you historically have in the vicinity of this house? Or what was the minimum area of a house you responded to, or the maximum price? And these features, they serve as great predictors for making a sort of a ranking. Then the question, of course, becomes, okay, how do we evaluate such a ranking model? And those of you who did ranking will probably know the normalized discounted cumulative gain and things like that. What's important to realize here is that evaluating a ranking task is not the same as evaluating a classification model. In a classification model, you have a simple answer, okay, this is classified wrongly or this is classified good. But in a ranking task, of course, if you put something at the first position or the second position, yeah, both are actually quite great if you have 60 results. But if you put something at position 20, that's already a lot worse than position 1 or 2. So we need to discount for that a bit. Well, for that we try to assign each response or click. And the response was, okay, I really want to rent this house. And the click is, I just viewed this house. A relevance, and based on that we try to with a sort of a discounting factor, try to compute, okay, how good is our ranking, and that gives us a metric. Again, this is a bit skewed, and here you see that we're doing much better than random, but this doesn't ring a bell, I think, to anyone. It's really hard to interpret these kinds of results. They're quite good for comparing models to one another. But if I say, yeah, I got a NDCG of 0.44, yeah, okay. Is that good? Yeah, I don't know. So it's much more insightful to look at these kinds of plots. And what you see here is, if we look at all houses that have been clicked, so all houses that have received a response of I want to rent this house, then you can, of course, try and plot, okay, at which positions were they ranked. So our model gives rankings, our model assigns ranks to a position, and then you can make these kind of plots. And if you then look at the orange bar, which is basically random, and the blue bar, which is our model, you see that we're able to put a lot of mass to the first positions there. And of course, this plot is quite closely related to things like the mean reciprocal rank, where this is basically the probability distribution of over your ranks, for those of you who did ranking. Yeah, I'll skip this, I think. There are of course, also you can, from a qualitative point of view, evaluate your model. So for example, if you look at the historic clicks, you can make a sort of a heat map. So, okay, where would I recommend a fixed house? So keeping the house the same and just moving it over the map, where would I recommend that? Yeah? Yeah. Yeah. We have a quite balanced set of users in terms of waiting time. So the distribution over those 12 years is quite the same. However, I do have to say that, of course, the users with a very long waiting time, longer than 12 years, they're scared, just because they can get a house quite easily. So in terms of that, we're quite balanced. But is that your question, or? You mean the behavior features, or the features? The features based on the behavior, we have features based on only the last 3 responses and the last 10 responses. So there's also, if your preferences changes indeed, and you have all the responses that are further away, that's accounted for. Okay, so what I said, we did something like that's called pairwise ranking, and we used the RankNet loss function. And basically, what you're doing when you're doing ranking, you're of course comparing items to one another. And now suppose I have 2 houses, I and J, well, suppose I want to model the probability that I should be ranked higher than J, and that's of course the case if I is more relevant, so if the relevance of I is higher than J. We can equip I and J both with a sort of a feature vector, say X. And in that X we can incorporate all those features we had. And those are features of the house itself, of course, so things like location, things like size, but also features of the user. So a part of those feature vectors for a specific query stays the same, the part of the user, of course, and that part of the house varies. And what we're then basically trying to model when we're doing pairwise ranking with that loss function we had, is we're trying to model the probability that I will be ranked higher than J. And how do we model that? Well, basically we try to estimate a function, f, and we just take the logistic function of the differences of the 2 function values there. Is this a bit clear? Yeah? Well, this, of course, you can optimize using something like cross entropy, or try and minimize the difference between these probabilities and your training set. And the cool thing now is, of course, that now you're not talking about a ranking task, but you're now talking about those pairwise probabilities. And that offers a new view of, you can talk about calibration of your model. So how are those probabilities calibrated? Do they match up with the actual probability? So the plot here shows that if I predict a probability that I will be ranked higher than J of 0.4, is the true proportion, if I take a sort of a bin around that, of houses of cases that I is ranked higher than J, also around 40%. So you can do a lot with those probabilities. And one nice thing is that those probabilities actually quantify the preference of a certain house over another house. So suppose I look from my perspective, and that means that a part of the feature vector are my features, like my historical behavior, my family situations, things like that. And I look at Jan's house, and then the other part, the part of the house of that feature vector, of course, are the features of the house. And then I can calculate the probability that once I compare my house to Jan's house, I can compare and calculate whether I will rank his house higher than my own house. And I can give it a probability. And I don't know, yeah, you don't know where Jan lives, but believe me. So that explicit probability is nice, because there you can work with. And that is a sort of a proxy for preferences over houses. And basically what you can do with that, oh boy, we shouldn't have copied them. It's all... basically what you can do with those probabilities is, of course, you can reason from every person who's currently living in social housing in the market somewhere. So I can reason from my point of view, and I can calculate the probability that I will prefer Jan's house or prefer Eduardo's house, but I can also reason from, for example, the point of view of Jan, that he will prefer Eduardo's house or my house. And basically that allows you to find a sort of graph structure. And yeah, this is of course a pruned version of that graph where we only kept the very high probabilities. But basically what you see that for each pair of nodes there you can get a directed edge, and that edge can be weighted with that probability. And what the nice thing about this is that if you do this, you already see some cycles appearing. For example, in this example, you could say, okay, Dave prefers Tim's house, or is likely to rank Tim's house higher than his own house. Tim is likely to rank Annika's house higher than his house, and Annika is likely to rank Dave's house higher than her own house. So basically, this is a sort of, with this you could make a suggestion to Dave, okay, hey, wouldn't you like to move to Tim's house? And Tim, wouldn't you like to move to Annika's house? And this is basically the idea we're working with. So from that ranking model, which you of course can employ to make a sort of a recommended system on the website and give users a personalized ordering or something, which is a great feature and it's all nice. But you can also take it a step further by looking at those pairwise probabilities to make some sort of a graph structure. And that graph structure is really powerful because it helps you to identify possibilities for movements in the social housing market and therefore achieve a better allocation. Well, there's of course a whole field of how you can do this, and if you would be living in some kind of banana republic, you probably say to all those users, okay, we disown you of your house and we allocate you the best house we think there is. Unfortunately, I don't know, yeah, we can't do that. So we need to find a way of making this stable, because you can imagine that even though those probabilities were nicely calibrated, as we saw, that only one of those edges needs to be infeasible, or Dave says, okay, yeah, Tim's house, that's all nice indeed on paper, but in practice, yeah, the neighbors, they're so loud, I don't want to move there. So we need to find a way of making this workable and working with some kind of backups. So finding cycles that are, that can be backed up by other cycles, which are still, where there's still preferences. And this is what Jan's going to talk about.
Yeah, so we have basically two questions. First of all, how do we even find the cycles? Because we did this for 3,000 people, and then you get like 3,000 people, and between all those people you get lines. So you cannot really do that by hand. So we have to find an algorithm to first find the cycles and then select the sort of the good cycles, the cycles with a high value. Well, so first to select the cycles or to find the cycles, we use a depth first search with two stopping criteria: that the length of the path is smaller than 6, and that the probability of the path is bigger than 0.6. Well, this is all quite technical, but what it means is basically this is just an algorithm, and it will give us all the cycles in the graph. It takes a while to calculate them. Of length bigger than 6 and smaller than 6, and with a probability higher than 0.6. Why 6? That's just the number we choose now. And if you take bigger than, like the bigger you take the cycles, like the algorithm starts taking longer and longer and longer. So we stopped at some point. Oh, this is something very wrong with the layout. Anyway, so that's what the algorithm does. And of course now we have a lot of cycles. As you can see, we did it with 3,000 people and we found 120,000 cycles. So and then of course people are involved in many cycles, but we don't want to send people around 40 emails. That seems a bit excessive. So we want to sort of find the cycles where we think we have the best chance of success. That's what Floris told us a bit. So how do we select those cycles? Well, we have first just a basic cycle, and if you look at the cycle, you think, oh well, that's a good cycle. There are like lots of high chances there. But it's good to realize that those probabilities are also they're the chances of responding to a house on a website. So that's something different from accepting a house. There could be like really personal circumstances that we cannot account for in the model. For example, maybe Julia thinks, well, Kay's house is very nice and all, but the neighbors have a very loud dog, and I'm very sensitive to noise, so I'm just not going to live there, even though I would respond to the house on the website. So to not ruin, like suppose it happens, and then whoa, that's gone. But like then this whole movement would be ruined. So we have sent 5 people an email, and then maybe some people get really excited about potentially moving house, but then they're all like, oh well, shit, it cannot happen because one movement is going on. So, but of course it's a full graph that we're looking at. So there are more potential movements. So maybe Julia is also interested in Pete's house, and that house also fits her personally. So that would be a backup. So then we could still have, and maybe she actually likes it, and then we still have movement. So then we still have success. Now, not everyone is involved, but we still have some success. So we want to really take this into consideration when we select the best cycles. So to now make this into an algorithm, what we say is that a graph with like many highly probable backups has more value. So to calculate the value of a graph, we run a Monte Carlo simulation. So how do we do that? We basically just remove edges at random, and then we do that 100 times. And we remove edges with the chance, well, of course, this chance, but then we take a conservative extra factor because we just don't know anything in the model. It's of course only responding to houses. And then the quality of the graph is defined, so we do this 100 times, and the quality of the graph defines the fraction of those 100 times that there's still a cycle possible. So those are all the highly probable graphs.
Wouldn't that favor then very complex systems in the first place where you can just always find a shortcut? What about
like huge graphs? Yeah, so that's a very good question. Actually, we take it slightly like we do divided by the length of the graph.
Okay.
And then, so we do a bit, but I wanted to keep it simple. So it's actually a lie, what I'm saying here. But it's very close to the truth. It's like it gets the idea of I think it's the core of the idea. So for example, this could be one trial, and then we see, oh well, here there's no success possible anymore because like there are lines here, but they're not in the right direction. So this would count as a fail in our Monte Carlo simulation. So this is the way how we then select the graphs. Well, we have run a simulation doing this. And that looked actually quite promising. So using this strategy to select the graphs, and then being conservative, so we say like then still like 40% of the movements don't happen, even if the chance is really high. We are able to move approximately 10% of the participants into Utrecht. So then we go more than triple the mutatiegraad. Don't really know what the English term for that is. But in Dutch, it's the percentage of houses that are changing hands every year, and that's at the moment 1/3 of that, more or less. Anyway, Floris has some next steps.
Yeah, thanks. Yeah, so as you can imagine, this is something that it can be quite political, and it touches on social housing, which is quite a political sector in the Netherlands, but also the municipality of Amsterdam and Utrecht have a say in this, the housing corporations, and even the state has some laws about, or I believe they're even at the European level, about who can live in what house and who should get assigned what house. So this idea and this experiment was already finished 6 months ago, but basically now we're working on trying to make this into an actual pilot with both the city of Amsterdam and the region of Utrecht, where we actually want to estimate, this idea seems nice on paper, but how does this work in practice? And how do those probabilities we've estimated transfer to the actual probabilities of moves? Because, like Jan said, those probabilities, they're based on ranking and based on preference. And of course, we only take people into account that have indicated, I want to move and I want to move to a better house. But yeah, how do they serve as a proxy for those moves and for the likelihood of those moves? So that's something we are working on, and we will be working on for quite a bit, I guess. And yeah, then all questions come to mind. What does that do with new entrants? Does it shorten the waiting time? Does it increase the waiting time because people stay longer in the social sector? So there's still a lot of open questions here to be asked, to which we also don't know the answer. But we still wanted to show, yeah, basically the idea of how you can transfer such a pairwise ranking model into such a graph structure. So that's basically it.
No questions for this? Oh, there are.
Have you taken into account the condition that you cannot move when you reach a certain salary?
Yeah.
Are these people not in the data at all?
If you reach a certain salary, we don't take you into account in construction of the graph. On top of that, you have some kind of regulation that's called passen toewijzen in het Nederlands. That means that you should get a house that fits your income. And we do take that into account in construction of the graph by just leaving out certain edges. Certain moves are not possible since somebody's income doesn't match such a house. Yeah.
So have you tried to do some sort of factorization in your features?
We did. We have, for example, some data on, or you mean factorization on the user level or on the level?
I mean, the features, they may depend exclusively, you know, they can be temporal as well, but they are only about you.
Yeah.
So have you tried to do any factorization to, let's say, combine your features with his features to try to see if that gives you something like a
So yes, a sort of collaborative filtering like scheme. We started with that, but we don't have any results on that. We had the idea indeed to be working on that, and of course, like you say, features are based on you, also on the house. But indeed, there's no information of Jan's responses in my predictions in that way. No, we used simply Network X, and we did it on a sample for Utrecht, like Jan said, about 3,000 participants. So that was still feasible, luckily. If we would do this in a larger setting, of course, and since that graph is full, we may need to look into something more powerful there. Yeah.
How many model iterations did you do before you came to this model? Did you try several things before, or did you first have this really big analysis round and you said, this is it?
I think this is the fifth iteration or something, and what we spent a lot of time figuring out is how to deal with some previous ordering being present in the data. We were lucky enough to have a sort of a randomized set on which we could test, so that's already a great thing actually. But for that, we experimented a lot with Bayesian things like, okay, the probability of that a house is also viewed by a user, because yeah, if he doesn't view a house, then he also won't respond to it and click to it. But actually, we ended up with a model that's simply using negative sampling. So basically, we keep all the clicks and the responses, and we downsample the negative part and make an ensemble of that. So we take 10 models on different faults based on that scheme and take an ensemble of that, and that worked best. But I think it's 5 iterations, something like that. Yeah.
Thanks.
Okay, thanks.
Thank you. I want to welcome Agis to the stage. Like this? Yeah, as high as possible.
Yeah.
Sound as best.
That's good?
Yeah.
Oh. Yeah. Yeah, I hope it's the last version. Yeah. I don't need a microphone, right?
No,
Hopefully.
It was fine without a microphone, I think.
Yeah?
Yeah.
All right. If I talk a bit lower, just tell me to go higher. Hello again to everybody. I'm glad to be here and share a nice and interesting experience we had while working at this case to one of our clients. The company was Freo, and it's a small group within Rabobank. And tonight, oh, what's this? Okay, sound with the format, right? Okay. Anyway, sorry. Tonight I'll dive into this case. It's about a loan application that Freo is doing. I'll go through the case step by step, and also the results, the benefits we had, and of course the challenges that we face at the end. Before this, a really quick introduction about me. My name is Agis, and based on my last name, you can see that I come from Greece. I'm a data scientist, and I work at Valid last 2.5 years. And I also, in my free time, I write something about data science in a blog, and you can see it here. You can visit the webpage later. So now let's dive to the case. Freo, as I told you, what was the past situation? It was the online department was a bit frustrated due to the lack of support from the IT, because the IT was their main focus was compliancy, so no budget for them to do something. So they turned to external partners, and because of the external partners, they were expensive and they didn't have a lot of experience in cloud solutions. They came to us, to Valid. And why did they choose us? We had a perfect match since the beginning. We had a great connection with employees, the agile way of working, experienced in cloud solutions, and of course, we offer real-time solutions, and we help them to achieve a higher conversion rate and stay ahead. This is our motto. And really a short introduction about my company. We are in the market for almost 20 years, and basically we're an IT service provider, 300 employees in 3 different locations, Maastricht, Eindhoven, and Utrecht, but our focus is not only in these cities, but in the whole country. And we offer this kind of solutions, hybrid solution in the cloud, modern workplace, data-driven business, and this will be our main focus today, the case that I will present to you. And of course, some innovative applications that will help our customers experience the modern technology or even create more innovative applications. So now, back to Freo. We did this case based on these 3 simple steps that we're doing for every client. Ready, set, stay ahead. Ready, we do some validation. We give advice about their infrastructure, their data, and we do some POCs, proof of concept, to prove that our technology and the solution really fits their need. We set architecture, data warehouse, and also some self-service BI. And the last step, stay ahead. Here's our case, most likely to convert application, of course, and by convert, I mean to get the loan at the end. So Freo, just a small introduction. If somebody needs a loan, goes to a bank, to a loan provider, or in this case to Freo.nl, fill in an application with his information, he requests a loan. In Greece, it's totally different. You just go to your parents if you need a loan. You don't go to the bank. And if you're lucky, they will give you the money. They will not ask them later. So what was the past situation? An applicant will go to the site, will fill in the applications, and then Freo will gather these applications, and they had an algorithm, let's say, but it's more like the rule of thumb. They say, okay, he's a trustworthy applicant, converted, approved. He's not, declined. And then they could further assist their applicants. So what we did, we analyzed a bit the behavior of the applicants based on their characteristics to identify some trends that may help assist them to get a loan at the end. And of course, based on this, we increased their conversion rate and some more sales through the internet. Of course, we just implement the solution, so it really needs to wait now and see the results, if they really boost their business or not. I hope they did. So really a quick example. So a new customer enters the site of Freo, fills in his application. This application goes through our model, and the model creates a predictive score. And based on this score, It classifies the applications, yes or no, did they get a loan or they don't. And then Freo could decide how they can assist more the applicants to make it easier for them to get a loan or not. We use on every case this standard process for every data mining project or data science. I'll go tonight through every step slowly. So first, the business understanding. For every project, you need to understand the business. You need to understand their needs, what's the problem, and what do they want to achieve at the end. So went to the domain experts, we talked about it, they gave us some information, and then after we understood their case, we tried to analyze all this and make a solution. Next step, and one of the most important, is to get the data, explore the data, and then if you can see these arrows, go back to the business, and because you understand the data, and then maybe you have some questions. So you need to go back to the business, to the domain experts, and ask them, okay, is this correct, is this wrong or not? So to really, really understand the data. Next step, prepare the data. Here, you really need to take your time, invest some time, because it's the most time-consuming step of every data science project. Because, as I like to say, even if you are the best data scientist, you create the best model, if you have garbage in, garbage will come out, for sure. So really, the data has to be very good prepared. So the input of the model has to be really nice and well done to input in the model. We did further some statistical analysis and some variables that we use for our model. As you can see, the requested loan of amount, the living situation of the applicant, is he living alone, is he living with a partner, their marital status, they are divorced, they are married, they are single, their age, of course, working experience in years, how many years they do this profession, etc. After you prepare your data, the next step, of course, is the modeling, where you create your model. And before you do this, you need to identify what kind of case you're working on, of course. Do you want to predict a numeric value? You'll do regression. Do you want to classify your data in two categories? Two-class classification, more, multi-class, etc. After this, after the case, it's the time to select the right algorithm. Here, of course, there's really big debate which algorithm is the correct, but I think the answer is always it depends. I can see some heads moving, so I think it's correct. So after the modeling, of course, you can see the arrows. You can go back to data preparation. You can retrain your model, of course, and go back to the modeling again, make some adjustments, and then you have the results. In this case, Freo, they got the results, and they were able really to see which applicants they were likely to convert at the end, at a really early stage of their application. After this, you create your model. You had some algorithms. It's time to evaluate the model. Compare the algorithm, because it's not always that you used only one algorithm, but you can use 2, 3, 4, compare them, and then see which one is best fits to your case, of course. After the evaluation, you can see this arrow. You go back to business understanding, so to domain experts again. Because maybe you have a result and it's not really logical. Is it correct? Is it not? So you communicate these results with your business experts, and then if you have the right answer, okay, last step, data presentation, deployment. We built this model in Azure, in Microsoft, and it's a platform, and it's really easy to set up a web service at the end. You create an API, and then you can call this API from Excel, from an application that you build, for instance, and you can use the percentage, for instance, of the case. And last step, of course, you can visualize your findings, a nice dashboard, for instance, to communicate your results. These some pictures from the model. I don't know if it's really visible here. Anyway, we'll share this presentation later, and then you can see. We built this in Azure, as I told you. It's like a data flow chart, and you can really see the inputs and preparation of the data, missing, cleaning the missing values, etc. At the end, the algorithms, score, and evaluation of the model. Here I put a picture of some key features with a score, and this score, it means, for instance, this feature, this variable, it's most likely to affect the predicted value of the model. At the evaluation step, this is, I think, it's familiar to you, it's the Roc Curve, and it shows how well your model performs. If it's like 50-50, it's this diagonal of the matrix. So as closer goes this curve to the end of the matrix, upper left corner, it means that it's better. If it's 100%, for sure it's something wrong. There is no 100% accurate algorithm. If you find it, join us, we're hiring. And here, because I said that the model creates a percentage, but also it classifies into classes, right? Here you have a threshold, for instance. If you put it 50%, any application that gets a score less than 50%, it's being classified to the non-converted application that they don't get the loan. If it's higher, of course, it got a loan. Results. So what we did with the statistical analysis, we could really answer some business questions like which month had the highest conversion rate, or which age group of the applicants had the highest conversion rate. Also, in which phase most of the applicants, the applications, they were declined. We also create, as an extra, a multi-class classification model here. And as input, we input all the applications that were declined, and then we could really predict in which phase during the application this application was declined or canceled. So benefits for our client. We try at least to increase the chance of conversion, and we just need to wait and see if this is true. And also, they got some insights of the applicant's behavior and real-time decision, because right now, for instance, a new application comes, gets the score, and really after 1 minute, you really know you have a likelihood, a percentage to know if this application at the end will convert or not. Of course, biggest challenge is was the data, to prepare the data and get the right data and agree on which data set we're going to use. For this case, we used 3 years of data of the applicant from 2015, 16, and 17. And to prepare the data, it was almost a nightmare, but it's as every data project, right? So this was the case. I hope it was very quickly, so I will not waste your time because it was the end of the night. Thank you. Questions? Oh, yeah, sure. Yes?
I wanted to understand, for this program, was it a black and white scenario where it may be declined?
Yeah, it was two-class classification. So all the applications get a score, as I told. If it's below 50, they didn't convert, didn't get a loan. It was higher than 50%, they got a loan. So 2 classes, yes, binary, like 0, 1, yes or no.
I was thinking maybe you could also, if somebody is going to be declined a loan,
Mm-hmm.
you could actually also enhance it by giving a suggestion, like if you had requested maybe 10,000 euros lower than what you requested, you would have
It's a solution, definitely, yes. Yes, it could be. Yes?
Are there any market influences here that in case there is not a lot of people looking for loans because there is simply no houses, that you sort of calibrated in a different way?
No. This was just with based on the data that Freo had it. So we didn't get any market insights, at least for now, for the moment, because it's like experimental solution, so we'll see. If it works, then of course you retrain the model and you add more variables that influence your solution. Thanks.
Why was it challenge to agree on data set?
Because of politics, of course. And because of the data, sometimes you have some sensitive data about these applicants, and it's not sure that they can share it with you and work with this data set. So this was a bit gray area to go there.
Are you also putting effort in trying to understand why a loan was denied?
Yes, this was the extra modeling, the multi-class that we did to see in which phase actually it was denied or declined by the bank. And then we do further analysis to see why actually, and because let's say that 60% of the applications, they were declined in a specific step, why this is happening. So we can do further investigation. But the real benefit is that Freo at the end, they want to use this application, this score, for instance, from the model, to see if an application gets like 10% to be likely to convert, and they can call them further and then say, okay, why? Do you need any further assistance? So can I help you with this? And at the end, to convert and get a loan, of course. Yes.
Did you go with Microsoft Azure over cloud or AWS?
Yes, I got this question from the client. We also use R and some Python to do, of course, some fine correlation, intercorrelation with the variables. But at the end, we built this model because it was easy to transfer it, to migrate to the client's environment, because they want to do it on-premise in their system. And with Azure, you can do this, and it's really easy to understand the flow chart, and then you can do improvements, you can train the model, and it's easier to explain this to some business people. I think we have 2 here. And it's really easy, yes, because if you just deliver code in R or in Python, it's really tough to make adjustments, and you need a lot of time. Yeah, you're welcome. I'll take it with me.
Thank you. So I just wanted to end at least the presentation part of the evening with a thank you all for coming. I hope you liked it. From my perspective, 3 very different presentations,